is the next chunk of next group of topics in 6033 called fault tolerance. And the goal here is to learn how to build reliable systems. In the extreme case, or at least our ideal goal, is to try to build systems that will never fail. And what we'll find is that we really can't do that, but what we'll try to do is to build systems which maybe fail less often than if you built them without the principles that we're going to talk about. So the idea is how to build reliable systems. So in order to understand how to build reliable systems, we need to understand what makes systems unreliable. And that has to do with understanding what faults are, what problems occur in systems that cause systems to fail. And you've actually seen many examples of faults already. Informally, a fault is just some kind of a flaw or an error or a mistake that causes a component or a module not to perform the way it's supposed to perform. And we'll formalize this notion a little bit today as we go along. So there are many examples of faults, several of which you've already seen. A system could fail because it has a software fault, a bug in a piece of software. So when you run it, it doesn't work according to the way you expect, and that causes something bad to happen. You might have hardware faults. You store some data on a disk, you go back and read it, and it isn't there, or it's been corrupted. That's an example of a fault that might cause bad things to happen if you build a system that relies on a disk storing data persistently. You might have design faults, where a design fault might be something where you try to, let's say, figure out how much buffering to put into a network switch, and you put into little buffering. So what ends up happening is too many packets get dropped. So you might actually just have a bad, some bad logic in there, and that causes you to design something that isn't quite going to work out. You might, of course, have implementation faults where you have a design and then you implement it and you've made a mistake in how it's implemented, and that could cause faults as well. And another example of a kind of fault is an operational fault, sometimes called a human error, where a user actually does something that you didn't anticipate or was told not to do, and that caused bad things to happen. Now, for all of these faults, there are really two categories of faults, regardless of what kind of fault it is. The first category of faults are latent faults. So an example of a latent fault is, let's say that you have a bug in a program where instead of testing if A less than B, you test if A greater than B. So that's a bug in a program. But until it actually runs, until that line of code runs, this fault in the program isn't actually going to do anything bad. It isn't going to have any adverse effect. And therefore, this fault is an example of a latent fault. Nothing is happening until it gets triggered. And when it gets triggered, that latent fault might become an active fault. Now, the problem when a latent fault becomes an active fault is that when you run that line of code, you might have a mistake coming out at the output, which we're going to call an error. So when an active fault is exercised, it leads to an error. And the problem with errors is that if you're not careful about how you deal with errors, and most of what we're going to talk about is how to deal with errors, if you're not careful about how you deal with errors, that leads to a failure. So somewhat more formally, a fault is just any flaw in an underlying component or an underlying subsystem that your system's using. Now, if the fault turns out not to be exercised, then there's no error. There's no error that results, and there's no failure that results. It's only when you have an active fault that you might have an error, and when you have an error, you might have a failure. And what we're going to try to do is to understand how to deal with these errors. So when errors occur, we're going to try to hide them or mask them or do something such that these errors don't propagate to cause failures. So the general goal, as I mentioned before, is to build systems that don't fail. And so in order to build systems that don't fail, there are two approaches at a 50,000-foot level. one approach to build a system that doesn't fail is to build it out of, make sure every system is going to be built out of components or modules, and those modules are going to be built out of modules themselves. One approach might be to make sure that no module ever fails, that no component that you use to build your bigger system ever fails. And it'll turn out that for reasons that will become clear based on an understanding of the techniques we're going to employ to build systems that don't fail, it'll turn out this is extremely expensive. It's just not going to work out for us to make sure that, our disks never fail and memory never fails and, our networks never fail and so on. It's just too expensive and nearly impossible. So what we're going to do actually is to start with unreliable components. And we're going to build reliable systems out of unreliable components or modules more generally. What this means is that the system that you build had better be tolerant of faults that these components, these underlying components have, which is why the design of systems that don't fail or rarely fail is essentially the same as designing systems that are tolerant of faults, hence fault tolerance. So that's the reason why we care about fault tolerance. So let's take an example of the kinds of, just to crystallize these notions of faults and failures a little bit more. So let's say you have a big system that has a module, let's call it M1, and this module uses a couple of other modules, M2 and M3. And let's say M2 uses another module, M4, where uses might be an invocation or, imagine this is an RPC call, for example. And let's say that M4 in here has some component inside M4, like a disk or something, some piece of software in M4, and let's say that that fails. So it has a fault, it gets triggered, it becomes active, leads to an error, it actually fails, that little component. So when this fault becomes a failure, a couple of things could happen. M4, which is the module to which this little failure belongs, can do one of two things. One possibility is that this fault that caused a failure gets exposed to the caller. So M4 hasn't managed to figure out a way to hide this failure from M2, which means that the fault propagates up, the failure gets visible, and the fault propagates up to M2. And now M2 actually sees the underlying component's failure. Now the point here is that this little component fault caused a failure here, which caused M4 itself to fail, because M4 now couldn't hide this underlying failure and reported something that was a failure, that was an output that didn't conform to the specification of M4 out to M2. Now, as far as M2 is concerned, all that has happened so far is that the failure of this module M4 has shown up as a fault to M2, right? Because an underlying module has failed, it doesn't mean that M2 has failed. It just means that M2 has now seen a fault. And M2 now might manage to hide this fault, which would mean that M1 doesn't actually see anything. It doesn't see the underlying fault that caused the failure at all. But of course, if M2 now couldn't hide this or couldn't mask this failure, then it would propagate an erroneous output out to M1, an output that didn't conform to the specification of M2, leading M1 to observe this as a fault, and so on. So the general idea is that failures of submodules tend to show up as faults in the higher level module. And our goal is to try to somehow design these systems that use lots of modules and components where at some level in the end, we would like to avoid failing overall. But inside here, we won't be able to go about making everything failure free. I mean, there might be failures inside submodules, but the idea is to ensure or to try to ensure that M1 itself, the highest level system, doesn't fail. So let's start with a few examples. In fact, these are all examples of things that we've already seen, and even though we haven't discussed it as such, we've seen a lot of examples of fault tolerance in the class so far. So, for example, if you have bad synchronization code, like you didn't use the locking discipline properly or didn't use any of the other synchronization primitives properly, you might have a software fault that leads to the failure of a module. Another example that we saw when we talked about networking is when we talked about routing, where the idea in here was that we talked about routing protocols that could handle failures of links. So certain links could fail, leading to certain paths not being usable, but the routing system managed to find other paths around the network. And that was because there were other paths available, because the network itself was built with some degree of redundancy underneath, and the routing protocol was able to exploit that. Another example that we saw again from networks is packet loss. We had best effort networks that would lose packets, and it didn't mean that your actual transfer of a file at the end-to-end layer would miss data. We came up with retransmissions as a mechanism to use, again, another form of redundancy where you try the same thing again to get your data through. Another example of a failure that we saw was congestion collapse. Where there was too much data being sent out into the network too fast, and the network would collapse. And our solution to this problem was really to shed load, was to run the system slower than it otherwise would by having the people sending data send data slower in order to alleviate this problem. Another example which we saw last time was, or briefly saw last time, was the domain name system, where domain name servers are replicated. So if you couldn't reach one to resolve your domain name, you could go to another one. And all of these, or most of these, actually use the same techniques that we're going to talk about. And all of these techniques are built around some form of redundancy or another, except probably the locking thing. But all of the others are built around some form of redundancy. And we'll understand this more systematically today and in the next couple of classes. So our goal here is to develop a systematic approach. To building systems that are fault tolerant. And the general approach for all fault tolerant systems is to use three techniques. And the first one we've already seen, which is don't build a monolithic system, always build it around modules. And the reason is that it'll turn out to be easier for us to isolate these modules, firstly, one from another, but then when modules fail, it'll be easier for us to treat those failures as faults and then try to hide those faults and apply the same technique. Which brings us to the second step, which is when failures occur causing errors, we need a plan for the calling module, for the higher level module, to detect errors. So failure results in an error. We got to figure out a way to make sure, we have to know that it's happened, which means we need techniques to detect it. And of course, once we detect an error, we have a bunch of things we could do with it. But ideally, if you want to prevent a failure of that system, of a system that's observed errors, you need a way to hide these errors. The jargon for this is mask errors. And if we do this, if we build systems that do this, then it's possible for us to build systems that conform to spec. So the goal here is to try to make sure that systems conform to some specification. And if things don't conform to a specification, then that's when we call it a failure. And sometimes we'll play some tricks where in order to build systems that, quote, never fail, we'll scale back the specification to actually allow for things that, would in fact be considered failures, but are things that still would conform to the spec. So we'll relax the specification to make sure that we could still meet the notion of a failure-free system or a fault-tolerant system. And we'll see some examples of that actually in the next lecture. And the general trick, I've already mentioned, the general trick for all of these systems that we're going to study, examples that we're going to study, is to use some form of redundancy. And that's the way in which we're going to mask errors. And almost all systems, every system that I know of that's fault tolerant uses redundancy in some form or another. And often it's not obvious how it uses it, but it does actually use redundancy. So I'm going to now give an example that will turn out to be the same example we'll use for the next 3 or 4 lectures. And so you may as well, you should probably get familiar with this example because we're going to see this over and over again. It's a really simple example, but it's complicated enough that everything we want to learn about fault tolerance will be visible in this example. So it starts with a person who wants to do a bank transaction at an ATM or a PC or on a computer. You want to do a bank transaction. And the way this works, as you probably know, is it goes over some kind of a network. And then, if you want to do this a bank transaction, it goes to a server, which is run by your bank. And the way this normally works is that the server has a module that it uses, a database system, which deals with managing your account information. And because you don't want to forget, and the bank shouldn't forget how much money you have, there's data that's stored on disk. And we're going to be doing things that are actions of the following form. We're going to be asking to transfer, from some account to another account some amount of money. And now, of course, anything could fail in between. So, for example, there could be a problem in the network, and the network could fail, or the software running on the server could fail, or the software running in this database system could crash, or report bad values, or something, the disk could fail. And we want systematic techniques by which this transfer here, or all these these calls that look a lot like transfer, do the right thing. And so this doing the right thing is actually what is an informal way of saying meet a specification. So we first have to decide what we want for a specification that has to hold true no matter what happens, no matter what failures occur. So one example of a specification might be to say, no matter what happens, if I invoke this and it returns, then this amount of money has to be transferred from here to here. So that could be a specification that you might expect. It also turns out that specification is extremely hard to meet, and we're not even going to try to do it. And this is the weasel wording I said before about we'll modify the specification. So we'll change the specification going forward for this example to mean if this call returns, then no matter what failures occur, either a transfer has happened exactly once, or the state of the system is as if the transfer didn't even get started. Okay, which is reasonable. I mean, and then if you really care about moving the money and you determine that it hasn't been moved, you or some program might try it again, which actually is another form of using redundancy where you just try it over again. And the reason, and we won't understand completely why a specification that says you have to do this exactly once if it returns, why that's hard to implement, why that's hard to achieve. We'll see that in the next couple of classes. So for now, just realize that the specification here is it should happen exactly once, or it should be as if it didn't even, no partial action corresponding to the internals of this transfer happened. So the state of the system must be as if the system never saw this transfer request. So any module could fail here. So let's take some examples of failures in order to get some terminology that will help us understand faults. So one thing that could happen is that you could have a disk failure. So the disk could just fail. And one example of a disk failure is the disk fails and then it just stops working, and it tells the database system that's trying to read and write data from it that it isn't working. So if that kind of failure happens where this module here or this component just completely stops and tells the higher level module that it stopped, that's an example of a failure that's called a fail-stop failure. And more generally, any module that tells the higher level module that it's just stopped working without reporting anything else, no outputs, that's fail-stop. Because you could have disks, and most disks today, you might have failures that aren't fail-stop. You might have something where there's some kind of error checking associated with every sector on your disk, and the disk might start reporting errors that say that this is a bad sector. So it doesn't fail-stop, but it tells the higher level, the database system in this case, that some data it's read or data that's been written, there's a bad sector, which means that the checksum doesn't match the data that's being read. When you have an error like that, where it doesn't stop working, but it tells you that something bad is going on, that's an example of a failure that's called a fail-fast failure. I actually don't think most of these terms are particularly important. Fail-stop is usually important and worth knowing. But the reason to go through these terms is more to understand that there are various kinds of failures possible. So one case, it stops working. In another case, it just tells you that it's not working but continues working. It tells you that certain operations are not, haven't been correctly done. Now, another thing that could happen when, for example, the disk has, has fail fast, is that the database system might decide that write operations. It doesn't really, you're not allowed to write things to disk because the disk is, either failed completely or has failed fast. But it might allow read-only actions or requests that are read-only. So, for example, it might allow users to come up to an ATM machine and just read how much money they have from their account, because it might be that there's a cache of the data that's in memory in the database. So it might allow read-only actions, in which case the system's is functioning with only a subset of the actions that it's supposed to be taking. And if that happens, that kind of failure is called a fail-soft failure, where it doesn't, not all of the interfaces are available, but a subset of the interfaces are available and correctly working. And the last kind of failure that could happen is that, for example, in this example, let's say that failures are occurring when there's a large number of people trying to make these requests at ATMs, and there's some problems that have arisen, and somebody determines that the problem arises when there's too many people gaining access to the system at the same time. And the system might now move to a mode where it allows only a small number of actions at a time, a small number of concurrent actions at a time, or maybe one action at a time. So one user can come at a time to the system, which means the system's, there has been a failure, but the way the system's dealing with it is that it determines that the failure doesn't get triggered when the load is low. So it might function at low performance. It still provides all of the interfaces, but just at very low performance or at lower performance. And that kind of behavior is called fail-safe. So it's moved to a mode where it's just scaled back how much work it's willing to do and does it at degraded performance. Okay, so the plan now is for the rest of today. So from next lecture on, what we're going to do is understand the algorithms for how we go about and how you build systems that actually do one or all of these in order to meet the specification that we want. But before we do that, we have to understand a little bit about models for faults. In order to build fault-tolerant systems, it's usually a good idea to understand a little bit more quantitatively models of faults that occur in systems. And primarily, this discussion is going to be focused on hardware faults, because most people don't understand how software faults are to be modeled. But since all our systems are going to be built on hardware, typically, for example, disks are going to be really common, or network links are going to be common, and all of those conform nicely to models, it's worth understanding how that works. So, for example, a disk manufacturer might report that the error rate of undetected errors. So disks usually have a fair amount of error detection in them, but they might report that the error rate of undetected errors is, say, 10 to the minus 12th or 10 to the minus 13th. And that number looks really small. That says that, out of that many bits, maybe one bit is corrupted and you can't detect it. But you have to realize that given modern workloads, for example, take Google as an example that you saw from last recitation, the amount of data that's being stored in a system like that, or the world in general, is so huge that a 10 to the minus 13th error rate means that you're probably seeing some bad data in file that you can never fix or never detect, every couple of days. Network people would tell you that fiber optic links have an error rate of 1 error in 10 to the 12th. But you have to realize that these links are sending so many gigabits per second that 1 error in 10 to the 12th means something like there's an error that you can't detect maybe every couple of hours. What that really means is that at the higher layers, you need to do more work in order to make sure that your data is protected, because you can't actually rely on the fact that your underlying components have these amazingly low numbers, because there's so much data going on being sent or being stored on these systems that you need to have other techniques at a higher layer to protect if you really care about the integrity of your data. In addition to these raw numbers, there's 2 or 3 other metrics that people use to understand faults. The first one, and failures. The first one is the number of tolerated failures. So for example, if you build a system to store data and you're worried about disks failing or disks reporting erroneous values, you might replicate that data across many, many disks. And then when you design your system, one of the things you would want to analyze and report is the number of tolerated failures of disks. So for example, if you build a system out of 7 disks, you might say that you can handle up to 2 failed disks, something like that, depending on how you've designed your system. And that's usually a good thing to report, because then people who use your system can know how to provision or engineer their system, your system. The second metric, which we're going to spend a few more minutes on, is something called mean time to failure. And what this says is, it takes a model where you have a system that starts at time 0 and it's running fine, and then at some point in time it fails. And then when it fails, somebody, that failure is made known to an operator, or it's made known to some higher level that has a plan to work around it to repair this failure. And then once the failure gets repaired, it takes some time for the failure to get repaired, and once it gets repaired, it starts running again, and then it fails at some other point in the future. And when it goes through the cycle of failures and repairs, you end up with a timeline that looks like this. So you might start at time 0, and the system's working fine, and then there's a failure that happens here, and then the system's down for a certain period of time, and then somebody repairs the system, and then it continues to work, and then it fails again, and so on. And so for each of the durations of time that the system's working, let's assume it's starting at 0, each of these defines a period of time that I'm going to call TTF, or time to fail. Okay, so this is the first time to fail interval. This is the second time to fail. This is the second time to fail interval, and then this is a time to repair, and this is the third time to fail interval, and so on. And analogously, in between here, I could define these time to repair intervals, TTR1, TTR2, and so on. So the mean time to failure is just the mean of these values. There's some duration of time here, like 3 hours, the system worked, and then it crashed. That's TTF1, and then somebody repaired it. It worked now for 6 hours. That's TTF2, and so on. If you run your system for a long enough period of time, like a disk or anything else, and then you observe all these time to fail samples, that tells you, and take the mean of that, that tells you a mean time to failure. Now the reason this is interesting is that you could run your system for a really long period of time and build up a metric called availability. So for example, if you're running a website, and the way this website works is it runs for a while, and then every once in a while it crashes, or its network crashes, and people can't get to you. So you could run this for months or years on end, and then observe these values, and then you could run this every month. You could decide what the availability is and decide if it's good enough, or if you want to make it higher or lower. So you can now define your availability to be the total amount, the fraction of time that your system is up and running. The fraction of time that the system is up and running is the fraction of time on this timeline that you have this kind of shaded thing. Okay, so that's just equal to the sum of all of the time to failure numbers divided by the total time. And the total time is just the sum of all the TTFs and the TTRs. Okay? And that's what availability means. It's the fraction of time that your system is available is up. Now, if you divide both the top and the bottom by n, this number works out to be the mean time to failure divided by the mean time to failure plus the mean time to repair. So this is a useful notion because now it tells you that you can watch your system for a really long period of time and build up a mean estimate of mean values of the time to failure and the time to repair, and just come up with a notion of what the availability of the system is, and then decide based on whether it's high enough or not, whether you want to improve some aspect of the system and whether it's worth doing. So it turns out this mean time to failure and therefore availability is related for components to a notion called the failure rate. So let me define the failure rate in a second. So the failure rate is defined as, it's also called a hazard function. That's why people use the term h of t, the hazard rate. That's defined as the probability that you have a failure of a system or a component in time t to t plus delta t, given that it's working, I'm going to say OK, at time t. Okay? So it's a conditional probability. It's a probability that you fail in the next time instant, given that it's correctly working and has been correctly working. It's correctly working at time t. So if you look at this for a disk, most disks look like the picture shown up here. This is also called the bathtub curve because it looks like a bathtub. What you see at the left end here are new disks. So the x-axis here shows time. I guess it's a little shifted below. You can't read some stuff that's written at the bottom. But the x-axis shows time and the y-axis shows the failure rate. So when you take a new component, like a new light bulb or a new disk, and anything new, there's a pretty high chance that it'll actually fail. This is why if you buy, manufacturers, when they sell you stuff, don't actually sell you things without actually burning them in first. Yeah, so for semiconductors, that's also called yield. They make a large number of chips, and then they burn in a few, and then they only give you the rest. And the stuff that's, survived the burn-in is the fraction that survives the burn-in is also called the yield. So what you see on the left, the colorful term for that is also infant mortality. So it's, things that die when they're really, really young. And then once you get past that early mortality period, you end up with a flat failure, a conditional probability for failure. And what this says is that, and I'll get to this in a little bit, but what this says is that once you're in the flat region, it says that the probability of failure is essentially independent of what's happened in the past. And then you stay here for a while, and then if the system has been operating, like a disk has been operating for a while, let's say 3 years or 5 years typically for disks, then the probability of failure starts going up again because that's usually due to wear and tear, which for hardware components is certainly the case. There are a couple of interesting things about this curve that you should realize, particularly when you read specifications for things like disks. Disk manufacturers will report a number like a mean time to failure number. And the mean time to failure number that they report might usually, for disks might be 200,000 hours or 300,000 hours. That's a really long period of time. That's 30 years. So when you look at a number like that, you have to ask whether what it means is that disks really survive 30 years. And if anybody who's owned a computer knows that their disk, has never, most disks don't survive 30 years. So they're actually reporting 1 over the reciprocal of this thing at the flat region of the curve, because this conditional failure probability rate at this operation time when the only reason things fail is completely random failures, not related to wear and tear. So when disk manufacturers report a mean time to failure number, they're actually reporting something that isn't that that's the time that your disk is likely to work. What that number really says is that during the period of time that the disk is normally working, the probability of a random failure is 1 over the mean time to failure. So that's what it really says. So the other number that they also report, often in smaller print, is the expected operational lifetime. And that's usually something like 3 years or 4 years or 5 years, whatever it is they report. And that's where this thing starts going up and get beyond a point where the probability of failure is above some threshold. They report that as the expected operational lifetime. Now, for software, this curve doesn't actually apply because, or at least nobody really knows what the curve is for software. What is true for software, though, is infant mortality, things where the conditional probability of failure is high for new software, which is why you're sort of well advised not to, the moment a new upgrade of something comes around, most people who are prudent wait a little bit to just make sure that all the bugs are ironed out and things get a little bit stable. So they wait a few months. You're always a couple of revisions behind. So I do believe that for software, the left side of the curve holds. It's totally unclear that there is a flat region, and it's totally unclear that things start rising again with age. So the reason for this curve being the way it is a lot of this is based on the fact that things are mechanical and have wear and tear. But the motivation for this kind of curve actually comes from demographics and from human lifespans. So this is a picture that I got from, it's a website called mortality.org, which is a research project run by demographers, and they have amazing data. There's way more data available about human life expectancy and demographics than anything about software. What this shows here is actually the same bathtub curve as in the previous chart. It just doesn't look like that because the y-axis is on a log scale. So given that it's rising linearly between 0.001 and 0.01 on a linear scale, that looks essentially flat. So human beings, for the probability of death given at a certain time, given that you're alive at a certain time, that follows this curve here, essentially a bathtub curve. At the left end, of course, there's infant mortality. This, I think, I pulled the data down. This is from an article that appeared where the data is for the US population in 1999. It starts off again with infant mortality, and then it's flat for a while, and then it rises up. Now, there's a lot of controversy, it turns out, for whether the bathtub curve at the right end holds for human beings or not, and some people believe it does, and some people believe it doesn't. But the point here is that for human beings anyway, the rule of thumb that insurance companies use is for determining insurance premiums is that the log of the death rate, the log of the probability of dying at a certain age is linear, grows linearly with the time that somebody's been alive. And that's what this graph shows, that on a log scale on the y-axis, you have a line. And that's what they use for determining insurance premiums. OK, so the reason this bathtub curve is actually useful is, so if you go back, let's go back here. The reason both these numbers are useful, the flat portion of the bathtub curve and the expected operational lifetime, is the following. It's not like this flat portion of the curve where the disk manufacturer reports a mean time to failure that's 30 years. It's not like that's useless, even though your disk only might run for 3 to 4 years. The reason is that if you have a project, if you have a system where you're willing to upgrade your disk every 3 years, where you've budgeted for upgrading your disks every, say, 3 years, then you might be better off buying a disk whose expected lifetime is only 5 years, but whose flat portion is really low. So in particular, if you're given 2 disks, one of which has a curve that looks like that, and another that has a curve that looks like that, and let's say this is 5 years and this is 3 years. If you're building a system and you've budgeted for upgrading your disks every 4 years, then you're probably better off using the thing with the lower value of mean time to failure, because its expected lifetime is longer. But if you're willing to upgrade your disks every 2 years or 1 year, then you might be better off with this thing here with the lower mean time to failure, even though its expected operational lifetime is smaller. So both these numbers are actually meaningful, and it depends a lot on how you're planning to use it. I mean, it's a lot like spare tires on your car. I mean, the spare tire will run perfectly fine as long as you don't exceed 100 miles. And the moment you exceed 100 miles, then you don't want to use it at all. And it might be a lot cheaper to build a spare tire that runs just 100 miles, because the use is you're guaranteed that you'll get to a repair shop within 100 miles. It's the same concept. Okay. So one of the things that we can define once we have this conditional failure rate is the reliability of a system. And we'll define that as the probability R of t is the probability that the system is working at time t, given that it was working at time 0, or more generally that, assuming that everything is always working at time 0, it's the probability that you're okay at time t. And it turns out that for components in the flat region of this curve where the h of t, the conditional failure rate, is a constant, on systems that satisfy that and which satisfy the property that the actual unconditional failure rate is a memoryless process where the probability of failure doesn't depend on how long the system has been running, it turns out for the systems that satisfy those conditions, which apparently disks do in their operation when they're actually not at the right edge of the curve, which disks do, the reliability is, this function goes as a very nice simple function, which is an exponential decaying function, e to the minus t over mttf. And this is under two conditions. H of t has to be flat, and the unconditional failure rate has to be something that doesn't depend on how long the system's been running. And for those systems, it's not hard to show that your reliability is just an exponential decaying function, which means you can do a lot of things like predict how long the system is likely to be running and so on. And that'll tell you, when to upgrade things. Okay, so given all of this stuff, we now want techniques to cope with failures, cope with faults, and that's what we're going to be looking at for the next few lectures. Let's take one simple example of a system first. And like I said before, all of these systems use redundancy in some form. So, if a disk fails at a certain rate, just put in multiple disks, replicate the data across them, and then hope that things survive. So the first kind of redundancy that you might have is in the example that I just talked about, is spatial redundancy, where the idea is that you have multiple copies of the same thing, and the games we're going to play all have to do with how we're going to manage all these copies. And actually, this will turn out to be quite complicated. We'll use these spatial copies in a number of different ways. In some examples, we'll apply error-correcting codes to make copies of the data, or use other codes to replicate the data. We might replicate data make copies of data in the form of logs, which keep track of, you run an operation, you store some results, but at the same time, before you store those results, you also store something in a log. So if the original data went away, your log can tell you what to do. Or you might just do plain and simple copies followed by voting. So the idea is that you run you have multiple copies of something, and then you write to all of them. In the simplest of schemes, you might write to all of them, and then when you want to read something, you read from all of them, and then just vote and go with the majority. So intuitively, that can tolerate a certain number of failures. So, and all of these approaches have been used, and people will continue to build systems along all of these ideas. But in addition, we're also going to look at temporal redundancy. And the idea here is try it again. So this is different from copies. What it says is you try something. If it doesn't work and you determine that it doesn't work, try it again. So retry is an example of temporal tricks. But it'll turn out we'll also use not just moving forward and retrying something that we know should be retried. We'll also use the trick of undoing things that we have done. So we'll move both directions on the time axis. We'll retry stuff, but at the same time, we'll also undo things, because sometimes things have happened that shouldn't have happened. Things went halfway, and we really want to back things out. And we're going to use both of these techniques. So one example of spatial redundancy is a voting scheme. And you can apply this to a bunch of many different kinds of systems, but let's just apply it to a simple example of, there's data stored in multiple locations, and then, whenever data is written, it's written to all of them, and then when you read it, you read from all of them, and then you vote. And in a simple model where these components are fail-stop, which means if they fail, they just fail. Well, excuse me. On a simple model where these things are not fail-stop or fail-fast, but just report bad data to you. So, you're voting on it, and these results come back. You've written something, and then when you read things back, arbitrary values might get returned if there's a failure, and if there's no failure here, correct values get returned. Then as long as 2 of these copies are correctly working, or 2 of these versions are correctly working, then the vote will actually return to you the correct output. And that's the idea behind voting. So if the reliability of each of these components is some R, that's the probability that the system is working at time t, according to that definition of reliability, then under the assumption that these are completely independent of each other, which is a big assumption, particularly for software, but might be a reasonable assumption for something like a disk, under the assumption that these are completely independent, then you could write out the reliability of this 3 voting scheme, of this thing where you're voting on 3 outputs. You know that the system is correctly working if any 2 of these are correctly working. So that happens under 2 conditions. Firstly, all 3 are correctly working, right? Or some 2 of the 3 are correctly working, and there's 3 ways in which you could choose some 2 of the 3. And one of them is wrongly working. And it turns out that this number actually is very, very large, much larger than R when R is close to 1. And in general, this is bigger than R when each of the components has high enough reliability, namely bigger than half. And so, let's say that each of these components has a reliability of 95%. If you work this number out, it turns out to be a pretty big number, much higher than 95%, much closer to 1. Of course, this kind of voting is a bad idea if the reliability of these components is really low. If it's below 1/2, then chances are that you're more likely that 2 of them are just wrong, and you agree on that result, and it turns out to reduce the reliability of the system. Now, in general, you might think that you can build systems out of this basic voting idea, and it, for various reasons, turns out that this idea has limited applicability for the kinds of things we want to do. And a lot of that stems from the fact that these are not, in general, in computer systems, it's very hard to design components that are completely independent of each other. It might work out okay for certain hardware components, where you might do this voting or other forms of spatial redundancy that gives you these impressive reliability numbers. But for software, this independence assumption turns out to be really hard to meet. And there is an approach to building software like this. It's called inversion programming, and it's still a topic of research where people try to build systems, software systems, out of voting. But you have to pay a lot of attention and care to make sure that these software components, these that are doing the same function, are actually independent. Maybe written by different people, running on different operating systems, and so on. And that turns out to be a pretty expensive undertaking. Still sometimes necessary if you want to build something highly reliable, but because of its cost, it's not something that is the sort of cookie cutter technique for achieving highly reliable software systems. And so what we're going to see starting from next time is a somewhat different approach for achieving software reliability that doesn't rely on voting, which won't actually achieve the same degree of reliability as these kinds of systems, but will achieve a different kind of reliability that we'll talk about starting from next time.